Hello everyone, welcome to my paper. In social interactions, theory of mind is particularly crucial for intelligent behavior in highly non-stationary, agent-dependent social environments where interactions often require generalization beyond prior experience. We investigated a potential recurrent neural mechanism for theory of mind that is learned via social interactions, especially examining how this system could be used to help agents adapt to novel contexts. Matching pennies pits two players against one another in an iterative, binary choice, zero-sum game, and provides a versatile platform to simulate social interactions. We define multiple classes of opponents with qualitatively different behaviors, which can be seen in the following table. Please see the paper for further details on their formulation. There are 503 unique strategies total in the 8 classes. The training classes are shown in green. The agent that we train to play against these strategies is an advantage actor critic. At each time step, the 4-dimensional input of the agent's binary, reward, and choice from the previous time step is fed forward into an LSTM of size 128. The policy and value are directly read out from that. We train the network on 3 opponent classes, 310 opponents in total. Importantly, the network never knows the identity of its opponent. We introduce meta-learning by randomly swapping opponents out every 150 steps of the game, which we termed a block. Meta-learning, or learning to learn, teaches the network to self-correct from feedback using only recurrent neural dynamics. When the agent played against its training and testing opponents, its performance was not significantly different from an agent trained against only one category, and it exceeded that of an untrained agent for all opponents. In the figure on the left, the opponents to the left of the black line are training classes. Over a subset of opponents for which the agent's performance can be significantly greater than chance, we found that the multitask agent adapted its performance to the new opponent within only 20 time steps. So, after training against multiple classes of opponents, the network learned to quickly infer novel strategies and adapt its behavior accordingly. Next, we fit 2 logistic regression classifiers to predict the opponent identity from the recurrent activity in trials against opponents from different training classes. One classifier was trained and tested on activity from the same block, called within block, and one was trained and tested on separate blocks that occurred far apart in time. We found that we could robustly decode the type of training opponent with 95% accuracy after only 20 trials into a block, consistent with the time course of behavioral adaptation. This accuracy persisted throughout the washout period, as shown in the between block classifier. Next, we perturbed the recurrent neural activity within the classifier's subspace from one class region to another. Perturbation significantly disrupted the agent's performance. Reward dropped to random, and classification accuracy fell to 0. This indicates the causal contribution of the opponent representation to the agent's performance. To understand how the agent relates train and test opponents in order to generalize, we probed the network representation in the full recurrent space. For each opponent, we identified a unique recurrent state by marginalizing over recent reward and action sequences. We reduced the 503 opponent representations with the 2-dimensional t-snake shown on the left. This figure clearly identifies multiple groups of test opponents that are distinctly separate from the training set. For example, the teal cluster of epsilon Q learning opponents in the bottom right. With this result, we hypothesized 3 possible mechanisms of similarity-based generalization: template matching, in which the network adopts one of the learned strategies; interpolation, in which the network maps the novel opponent to one of the learned categories; and extrapolation, in which the network might use its learned representation beyond specific strategies or categories. We probe the mode of similarity-based generalization of each of the test opponents by comparing them to the training representations with 2 measures: the minimum Euclidean distance to a training representation in the y-axis, and the Euclidean distance to an LC opponent with parameters that best fit the test opponent strategy, LC mapping, on the x-axis. The results of this probe are plotted in the scatter plot on the right, where each shaded region represents a different general strategy. Further results do not depend on these specific boundaries, however. We found that the majority of training opponents, 129, fell in the template match region. Here, some are not pictured because they do not have a good LC mapping fit. 42 opponents were classified as extrapolation. We asked whether the training dynamics operated on a low-dimensional manifold and if the test dynamics also fell on that manifold. We performed PCA on recurrent states from all training opponents and calculated the explained variance ratio of the test states on these PCs. We identified that 95% of the training variance was explained by the first 10 PCs. These same PCs summarize roughly 92% of the variance for all test classes, indicating that their dynamics also lie in the training manifold. To investigate how the extrapolation opponents differ from the others, we asked how the dynamics along the first 2 PCs differ in the test states. We estimated the density of recurrent states using a Gaussian kernel density estimator and plotted the results in the heat map on the right. The majority of extrapolation states are localized in regions where there is low or zero density in the training case, also called WD here, near the edge of the overall distribution. Furthermore, roughly 50% of the cumulative density for the extrapolation distribution existed in regions of the training distribution that make up less than 5% of the density. This was not the case for other generalization types. These results suggest that the extrapolation states lie on the edge of the learned manifold in regions rarely occupied by the training states. In conclusion, by learning to interact in a competitive game against different types of opponents, we show that a recurrent neural network had developed a dynamical representation of strategy. Furthermore, the network had learned to use this representation to generalize via three mechanisms, perhaps most interestingly, what we call extrapolation, which is mixing and recombining information from the training opponent classes. These may be mechanisms by which neural systems solve the most important problem of theory of mind, which is adapting to novel social interactions. Thank you.